So my research project is about evaluation of a prediction model. So first of all, I'm going to talk about fundamental concepts and then how these can be applied to a specific problem. So a prediction model derives a prediction about a new object. But what is a prediction measure? It is a general rule that can assess the performance of a model. So also a program can be implemented by an algorithm that can perform a particular task or can learn from experience. So a program that can learn from experience can do a variety of tasks like recognition of handwriting, digits and faces, diagnosis patients in a hospital, estimating houses prices, among others. So this is the problem that where I'm going to apply a specific concepts, and it's a research problem. So it is there are 10 questions and they all can be answered by yes or no, and the task is to find the answers of the 10 questions in fewer steps as possible. So every time a guess is submitted, the feedback is just going to be the total amount of questions answered incorrectly. So why is this problem important? Because it is easy to understand, it is solvable, I can build a model from this, and I can evaluate its performance. So my assumptions about this is that my answer can be represented by a binary vector where no is denotated by a 0 and yes is denotated by a 1. From that I can get that I'll have 1024 binary sequences, that is 2 to the 10, and every sequence is equally possible to be the right answer. So the probability of getting one is 1 over 1024. So I have two methods to solve this problem, and the first one is just going to change one bit at a time, and it wouldn't the strategy that this method follows doesn't change from the feedback that it gets. It will just tell it like you have reached the right answer, but nothing else. It will follow the same steps in each case, no matter what the feedback is. So from this method I get that the best guess is 1 step and the worst case is 10 steps. So now I'm going to explain an example to explain this method. So the first, assuming that my true answer is just the first position 1 and the rest is 0, then my first guess is always going to be just all zeros, and then I'm changing one bit at a time. And if my incorrect answer is 2, I will keep changing one bit at a time till I get the correct answer. So how this works? At first, before I do any guess, I'll have 1024 sequences that can be all equally possible with a probability of 1 over 1024. So why I choose this first guess is because this will divide all my sequences in 11 partitions, because my feedback can be 11 different numbers from 0 to 10. And from this feedback I get that how many ones I have in my answer. So pretty much this is the partitions that I'll get. If my feedback is 0, I'll just have one sequence, so I'll get the answer in one step. And this is the distribution of all the 11 partitions, but in this specific example, I'll get one as a feedback, so I'll have 10 sequences. So after my first guess, I'll have 10 sequences with a probability of 1/10. And my second guess, I'll have 1 in the last position. That is my guess. So the only feedback that I get from this method is that if this is the right guess or not. That means that it will divide the partition in two, given if my feedback is 0, that's the correct sequence, but if the feedback is 9, if 2, I'll have 9 sequences remaining. So here it's just a bitwise comparison where I have my feedback as 0, and when I can have my feedback as 2, because the 1 can be in any of these positions. So if my feedback is 0, the bit 1 is in the position 10, and if the feedback is 2, is somewhere in the position 1 to 9. And this will keep going till my step 10, where before my step 10 I'll have just 2 sequences remaining with probability of 1/2, and if I get 0, that means that that's my right sequence, and if I get 2, it's my bit is in the first position. So this is a distribution about of how if my first feedback is 1, how many steps it will take me to guess each one of the combinations. So in the best case, I'll get my combination in 2 steps, and in the worst case in 10 steps. And the mean is 6.3. So now I'll show the second method, that is changing a bunch of bits at a time, and how this can improve the performance of the method, because it has adaptability, and the strategy that I'll follow depends on the feedback that I get in each guess. So with this method, I guarantees that the worst case is obtaining as fewer steps as possible. So I'll show an example to show how this works. It's the same, I just have 1 in my whole answer. So I begin with zeros, and then I'll keep dividing my vector in 2. So in the second step, I'll put 1s in the first half of my vector, and then half in the second one, and I'll keep going till I know exactly where my 1 is. So even in the worst case, I'll just get to 5 steps. So what is the consideration to do a guess is that I get the most of information from the feedback, and that I can divide my partition as much as possible. So from the first feedback, before my first feedback, I have the same space, 1024 sequences, and it'll be divided in 11 partition with my first feedback that is from my guess all zeros. But with my second guess, that is half 1s, I divide my sequences in 2 partitions, 4 and 6. And this will tell me where the 1 is, if in the first half or in the last half, in the right side. So if it is 4, I'll have 4 possible sequences. If it is 6, I'll have 5 possible sequences. So I know this because if the 1 is in the first half, it will give me 4 incorrect answers no matter where it is. And if my feedback is 6, I know that is in the other side, because I'll have these 5 1s incorrect and 1 from the other one that is correct. So after my second guess, I have reduced my possible sequences in half. So now I have 5 possible sequences. And the third guess is again divide the vector in 2. So I have the first part I'll fill it out with zeros and the second part with ones. So I have again divided my remaining sequences in 2. I can get as feedback as 2 or 4. And this will tell me if the one that I'm looking for is in the first 2 spots or in these 3 last spots. And this will know by making a bitwise comparison, and it will always be the same. So it will tell me exactly the position that, well, where I have to look for the one, so I don't have to spend the time looking anywhere, just in the bits that are more probable. So after the third guess, I have 3 possible sequences. After the fourth guess, I'll have 2 possible sequences, and it does pretty much the same. It divides the vector in 2. The vector that I know that my 1 is possible to be in, it is divided again in 2. After I get to the fifth guess, that my only 2 possible answers is that my 1 is here in my 4th position or in my 5th position. So I tested in those positions where I can get as feedback as 0 or 2. So even in the worst case, I'll have 5 steps, but in my best case, I'll still have to do 4 steps to get the right answer. But my mean is 404. So now I'm going to evaluate the performance of each method. So even though both has the same steps to get the worst case, the number of sequences that we'll need to do that amount of steps are much less in the second method. So in the first method, I need 512 sequences. We'll need to do 10 steps, but in the second method, less than 252 sequences will need to do the 10 steps. And the best case, both has the same, because it's when the feedback is 0 or 10 that you immediately know the answer. And the difference is basically if their adaptability, because the first one just do the same with every feedback, but the second one changes with a feedback that it gets. So a better method will be the second one, because it works on an online setting. It is that it improves as it gets more information about my answer. So my short-term goals will be to build a prediction model for a time series, as I did before with a time series that Bryce gave me. But now the difference is that I'll try to implement it with a conformal prediction and build a prediction measure to evaluate its performance. Thank you.
You demonstrate this 10-question guessing game. You only consider, for instance, the first guess has a feedback of 1, right?
Yes.
And what if you have other feedback? What's going to happen for method 1 and method 2?
In the first method, I will still do the 10 steps, no matter what the feedback is. But with the second method, it depends on the feedback. For example, if my feedback is 2, I'll have 45 sequences. So I need to do a different series of steps. And my worst case will be when my feedback is 5, because I have the most of the sequences that are 252. So in that case, I'll need to do the 10 steps to get the right answer, because I have more sequences.
So even with that feedback of 5, do you still think method 2 is better than method 1, or it depends?
It depends, I think.
So you think if the first guess gives you a feedback of 5, then you don't want to use your second method?
I think that still this method would be better, because even with this method, in the best case, I'll get my answer in the second step, because I always divide the vector in 2. So my second guess will be 5 ones, and I'll have one case in that situation, or the 5 ones in the last 5 position that I'll have another possible sequence.
In your opinion, what would be the principled way of measuring the performance of any method that claims to solve this 10-question guessing game?
The one that has the less possible sequences that have the worst case. I mean, if in one method I have 100 sequences that need to do the 10 steps, but in the other one I have 500 that need to do the 10 steps, then I'll say that a better method will be the second one, because
are you saying any method that solves 10-question guessing game needs to make 10 steps in the worst case?
Yeah. Yes, because it...
Can you prove that?
There's no other way to divide the array or the vector in the way that the partitions are, that you can get more partitions or they can be more balanced. So in the first case, I get like from the feedback, I guess 1 possible sequence and 9 possible sequences from the specific example. But in the second method, I have 5 sequences and 5 sequences. So this method, what does is to divide the possible sequences in a more balanced way, and there is no other way to divide the array in that way. You can test it 2 1s and 8 0s, but still you are going to get different partitions that will not give you as much information.
Let me ask one question. I'm not so familiar with I'm not so still with the second method, because so I'm going back in level of questioning. I'm not getting very deep right now. Just the first method is clear. The second method, I know that you're dividing in half of the time.
Mm-hmm.
Now, I'm not sure if I got this right. I mean, does this work for any kind of sequence of zeros and ones?
No.
Just if you're looking for a single one?
Well, each feedback will have its sequences. So if you see it as a tree,
Mm-hmm.
you'll have a lot of ramifications. So it really depends on the feedback that you get.
Okay. Yeah, because in the example, I mean, there was just a single one.
Mm-hmm.
So obviously it's clear to see that in the first case you get like, either 4 or 6, and then, but that method can be applied to any sequence, right?
Yes. Not exactly in that order,
yeah.
But the idea it's the same, that you divide yes, and you divide the part in 2 in where you know there is a 1, because you may have 3 1s in the whole vector, but still you are just going to look one at a time.
I see. So you're looking for 1s anyway. So if, for instance, if you split, let's say there's no 1s in the first half, then you don't worry about it anymore.
Yes.
But if you have some 1s, then you know how many, and then you're splitting until you find all of them.
Yeah.
So what is, in the general case, what would be the average, let's say, number of steps you would need to follow for the second method?
I don't
You don't
have
have
that
that?
yet.
Right. Because I was thinking, yeah. And then of course the distribution of the ones and zeros can be different. So for instance, could you split, instead of dividing in two every time, could you split, let's say, differently? I mean, in a non-uniform way, would it make sense? Depending on the number of ones and zeros we have on both sides. For example, let's say on one side we have, let's say it's not 10 ones, but let's say it's 100 maybe, or 10 is okay. So let's say you split it, and on one side you have a single one, and you know that on the other side you have 3 ones. I don't know. Should we divide differently? Maybe give it. You know what I mean? I don't know if that is something.
Yeah, you should. In fact, you have like 1,024 different possible guesses.
So
Each one you would expect several possible answers, which will bring you some information. And you will have to judge how much information you expect to have in order to say that whether that's a particular guess or not.
I was just thinking, because I don't know the problem, because again, as you said, it doesn't require scientific knowledge necessarily. So I guess I'm just thinking, I mean, for instance, if I knew because after you ask once, you kind of know how many ones and zeros on both sides. So I guess you can maybe try to make the probability uniform somehow. Maybe it's going to be easier. Maybe it's going to be faster this way, in average, I'm not sure. Or something like that. I'm just saying, I don't know. Because I know the problem. About the fish group, I didn't say much because I know the problem. So I'm now just trying to learn something.